Ladies and gentlemen, please welcome NVIDIA founder and CEO, Jensen Huang.
Welcome. We've been working really hard, and today is a historic moment. Today's a special day because this SIGGRAPH is Pixar RenderMan's 30th birthday. Over the course, the progress that they have made and the relentless pursuit for image perfection has been nothing short of amazing. 1995, Toy Story premiered using NURBS to generate characters, stochastic sampled AAs, motion blur. The imagery were just beautiful. It was processed with 800,000 CPU hours on a 100 megahertz, 27 megaflop Spark CPU. 100 megahertz. It's so cute. Several years later, with cars, they introduced ray tracing so that they could have beautiful reflections, beautiful shadows, ambient occlusion. In 2006, they used global illumination for the very first time. With global illumination, all of a sudden, light just works as it should. The subtleties of light bouncing all over the environment, picking up the color as it goes along, paints it just an amazing, amazing movie. They took it another step further with Finding Dory. All of a sudden, Dory's in a water environment. The rays are bouncing off of the waves in the water. The reflection, the refractions just exploded the amount of computation that was absolutely necessary to render that scene. And they invented something else. Using a state-of-the-art technology and deep learning, they created AI-based denoising. As a result, filling in all of the spots that the rays haven't reached yet. And as a result, reduced the amount of render time necessary tremendously. But even then, the amount of computation that was required is amazing. Now, of course, you guys know that for the last several years, Moore's Law has really come to an end. We can't get transistors to go any faster without consuming even more power. We've lost the ability to find any more instruction-level parallelism. We're running into walls left and right. As a result, CPU performance has really come to a halt, and you could see it here. But yet, the amount of computation, the amount of CPU hours that's consumed to render these movies continue to go up. Meanwhile, 25 years ago, this year, we started NVIDIA, and our pursuit was to generate the most amazing imagery in a 30th of a second, and at the price point that consumers would pay for. That curve looks like this. Our first contribution was the introduction of GeForce 256, the first GeForce, the first processor that did all of the geometry transformation, lighting transformation in hardware. And then several years later, in 2003, we introduced GeForce 3, the world's first programmable shader. And then in 2006, we introduced our single most important GPU ever, the world's first compute GPU, the first CUDA GPU. The rate of progress has been completely astounding. And the reason for that is this. We've been able to operate and optimize performance across the entire stack. By working with APIs and engines and software developers, we've been able to remove bottlenecks and innovate and create new ideas that makes it possible for us to break Moore's Law. And that's the reason why the accelerated computing law, the GPU accelerated computing law, has moved so much faster, but it requires us to all work as one team. This is the world's most demanding co-design challenge, where software developers, algorithm developers, tools developers are all working together to create one amazing experience. We've been pursuing the path to PHOTOREAL, and there are so much progress. Amazing amounts of geometry that is going to be in the scene, because the world's got lots of geometry, and some of it includes light and cast shadows, and the microstructure on the geometry allows us to pick up the subtleties of the light, causes that nice rim lighting. Using cameras with lots and lots of shots to reconstruct a photorealistic environment, to model and to create photorealistic textures. Creating materials that are physically based, metallic or dielectric, smooth or coarse, rough, translucency, subsurface scattering. All of these physically based properties are now possible for us to be modeled. simulating physics, soft bodies, rigid bodies, particles, fluids, springs and strings, because the world moves in a very predictable way. Character animation, using motion capture and then blending shapes. And now we're even able to teach a character with deep learning how to animate itself. Facial animation is incredibly important. This is digital Doug. And instead of using markers on your face to track your facial animation, now we could use AI to figure that out all by itself. And so making it easier for us to capture very realistic facial animation. All of this progress is made possible because the performance of our capabilities, the technology underneath, continues to advance. And working closely as one industry, we've been able to do amazing things. There's been one enormous roadblock. That roadblock is as fundamental as it can possibly be, and it's the simulation of light. We've been able to do all kinds of amazing things and make these amazing, beautiful video games, but we've been doing it through a lot of hackery. We've been placing lights that are invisible to you in the environments so that we could recreate what otherwise would be global illumination. This roadblock has been the endeavor of computer scientists and computer graphics engineers since Turner Whitted first wrote about it in 1979. Turner Whitted is now a researcher at NVIDIA. He described a really elegant algorithm called the multi-bounce recursive ray tracing algorithm. It casts a ray from your virtual eye through a virtual screen through that pixel, and it flies towards and either intersects a surface. When it intersects that surface, it creates a whole bunch of shadow rays in the direction of lights. And if the path of that shadow ray towards the light were to be occluded, meaning intersects another surface, it would be in shadow. Otherwise, it would be lit. But it goes further. If that surface was not diffused and it was reflective, it would generate a reflection ray. It would take into consideration the normal of that surface and the incoming angle of the ray, and then again, it would create that ray and it would follow the original algorithm, create other shadow rays, trace its way to the light. And if it turns out to be a refractive surface, it would obey Snell's law, and it would bend according to the medium, generate more rays, and then follow the original algorithm, hits another surface. If it intersects another surface, creates a whole bunch more shadow rays. And then when it's all done with that, it would figure out how to illuminate that surface by shading it. Well, it turns out this algorithm, as elegant as it is incredibly computationally intensive. And the reason for that is because there are billions of rays and there are millions and millions of polygons in the scene. And so computing it is extraordinary. Well, at the time that he wrote the paper, he used the VAX, at the time it was probably $1.5 million, and it took him 1.5 hours to simulate one frame. So he was basically doing about 60 pixels per second. These days we do 60 frames per second, but he does 60 pixels per second. He described that it would take a Cray computer behind every single pixel to generate real-time ray tracing. It turns out his estimates were pretty close. 35 years later, we're able to put effectively several Cray supercomputers behind every single pixel, and we created a brand new way of doing rendering, and we introduced it this year at GDC, the Game Developers Conference in March, for the very first time. It's a brand new rendering system. We call it the NVIDIA RTX. And it runs on a desk-side supercomputer we call the DGX Station. It requires 4 of our highest performance GPUs, the same GPUs that are now powering our nation's fastest supercomputer, the fastest supercomputer in the world, called the Tesla V100. It takes 4 of those, all connected together, working simultaneously, generating 5 rays per pixel to simulate what you're about to see in real time. Let's roll it.
What's the story with all the elevators lately? I heard Kylo Ren destroyed the one over in D sector.
If you ask me, who's ever in charge of this place should be transferred to Hoth. What? What? You think she heard us?
Yeah, I think she heard us.
At least we blend in for once.
Well, ladies and gentlemen, I have a surprise for you. It turns out it was running on this. One single GPU. Ladies and gentlemen, this is the world's first ray tracing GPU. Now, the concentration in my face is because the reflections on this graphics card works perfectly. We call it the Quadro RTX family. There's several versions of it. The performance is absolutely incredible. Up to 10 gigaраys per second. 10 gigaраys per second. Just to put it in perspective, the fastest CPU in the world with a whole bunch of cores in it can probably do a few 100,000, a couple of 200,000-300,000 rays per second. 10 gigarays per second. 10 gigarays per second. It's even fun to say. When was the first time that anybody ever used the word gigarays? We use teraflops, but we've never used the word gigarays. This is the world's first gigaray GPU. How many rays you got? Gigarays. Not only does it have an enormous amount of floating point performance for shading, also this shading architecture, this SM, our new compute architecture, has the first integer and floating point processing pipeline so that we could do address calculations and numerical calculations all at the same time. We perform up to 16 teraflops, and when was the last time you heard the word TIPS? 16 TIPS. And it comes with this brand new NVLink multi-GPU connector so that the frame buffer, every single GPU, the GPU could talk to every other GPU's frame buffer as of its own. Over this NVLink interface, 100 gigabytes, low latency, this incredible NVLink connector here. So the highest end Quadro, also powered by this Turing GPU, has 500 trillion tensor operations per second. No processor in the history of processors has ever commanded this much computational resource on one chip. 3 types of processors. The SM for compute and shading, a brand new processor called the RT core with 10 gigarays per second for ray tracing, and a new processor called the Tensor core for deep learning and AI. 500 trillion operations per second. The new Turing GPU is the greatest leap since 2006 when we introduced CUDA. This fundamentally changes how computer graphics is going to be done. It's a step function in realism. These are our goals, to make sure that whatever images are generated is dramatically different than what was possible before. That we invent a new computing model that takes advantage of the efficiencies of rasterization, but the realistic simulation of light for shadows and reflections and area lights, refractions, and all of those translucencies and all of those effects that are so difficult with rasterization, to combine it with compute and also artificial intelligence, to make all of this work together in an operable way. It has to be amazing at today's applications, but it has to be utterly awesome for tomorrow's. When you buy this GPU, you're going to enjoy it immediately, and you're going to be able to enjoy applications that will be coming very shortly that I'll show you in just a second. And just to take a look at what's inside this chip, so the Turing SM, 16 teraflops and 16 TIPS, does concurrent floating point and integer instructions at the same time, has a unified L1 cache, has variable rate shading. For foveated rendering, all kinds of new algorithms are possible. Motion adaptive shading, so when things are moving, you don't have to dedicate as much shading horsepower to it. For different areas that you might be able to reduce the amount of shading horsepower dedicated to it because the content's not changing very much. So all kinds of new algorithms are now possible so that we can conserve the shading horsepower to create and dedicate it and focus that computing resource where you might need it most. The RT core, 10 gigabytes per second, it has an accelerator that accelerates the BVH, the bounding volume hierarchy acceleration structure. Basically, when you look into a scene, there are all these geometries. The geometries are encapsulated in these bounding volumes. These bounding volumes are created in real time. And this bounding volume inside has subparts in the geometry, and they have sub-bounding volumes. When an ray intersects one box, you can dismiss all of the other boxes because they're not going to be in the ray. That allows you to figure out, as quickly as possible, test of all the rays that you're sending into the scene, which ray intersects with which surface and which primitive. That test is so computationally intensive. For the longest time, people thought that it would never be possible to do on a GPU until now. That's why it took 10 years of research. Figuring out exactly how to create this RT core, ray tracing core, that accelerates this data structure, this acceleration structure, to figure out exactly which one of the primitives that a ray intersects, and to interoperate with a shader was a great challenge. That was the amazing invention. As a result, we were able to achieve real-time ray tracing for the very first time. The Tensor Core has 3 different precisions. FP16, well, of course, it has FP32. It has 120 teraflops, 25 teraflops of FP16, 250 tops of Int8, and 500 tops of Int4. If you need precision, use FP16. 10 times the performance of Pascal. If you need less precision, use Int4. 10 times what was possible with Pascal. Incredible. The display is designed completely for HDR through and through and supports 8K displays. Video is designed to be able to encode 8K and to do so with the highest level of quality, reducing your bit rate. So if we wanted to stream graphics or remote graphics from far away, we could do so incredibly well for the very first time. And has this NVLink that connects multiple GPUs so that the frame buffer is essentially additive. If you compare it to Pascal, it looks a little bit like this. Pascal was 11.8 billion transistors, 471 millimeters squared, 24 gigabytes at 10 gigahertz. Turing is 1.6 times bigger, 19 billion transistors. It's the largest processor the world has ever made, short of just one other. And that one other is called the Volta V100, that's used to power supercomputers all over the world. Turing is 754 millimeters squared and has the ability to drive 48 plus 48 gigabytes of frame buffer, a giant frame buffer. If you compare it like this, 13 teraflops is now 16 plus 16 tips. Instead of having to wait between floating point or integer, we can now do floating point and an integer at the same time. Instead of 50 tops of Int8, we now have a tensor core that can either do 125 teraflops for precision inference or 500 tops of Int4. And then, of course, a brand new processor called RT Core. There's a brand new software stack. In order to bring all of this to life is software and algorithms and libraries and SDKs and tools. This is the first rendering architecture that supports this hybrid approach of rendering, interoperability between rasterization and ray tracing and compute and AI. It supports optics, Vulkan, and Microsoft DXR. There's a plug-in architecture for deep learning so that we could create models for super resolution, for example, for denoising, for example, for frame interpolation, for example. All kinds of new special effects are going to be possible because of this architecture, and it runs it on the Tensor Core. The Tensor Core is so fast, it makes it possible for us to create these really sophisticated models, deep learning models, and run it in real time. Today, we're also announcing that we're going to open source a really, really fantastic piece of work called the NVIDIA MDL, Material Description Language, a high-level programming language that captures the properties, the physical properties of materials and its reflectance functions, its metalness and dielectric, smoothness or roughness, all captured in this thing called a bidirectional reflectance scattering function. on first principles capture the properties of materials and makes it possible for us to then interchange it between applications. We're also announcing today that we're working closely with Pixar and we're going to support the universal scene description language so that content could move in and out of tools. Computer graphics reinvented, merging rasterization and ray tracing, compute, and AI. Well, our goal, of course, is to create amazing imagery. This is a wonderful way to inspire us, the Cornell box. It was designed so that it's easy for us to compare and determine the accuracy of a rendered image to images that was taken from a camera. Let's show you what today's computer graphics looks like. So we're going to step through this very quickly, just give you a sense of the progress of computer graphics. This is traditional graphics, and this is a point light, and you have different materials on it. The red is leather, white is cement, and the green ball there looks like clear coat, car paint, green car paint. And you can see that the point light is casting shadows, and those shadows are, well, they look rather hard, and it's made out of shadow maps. And so let's go take it to another step, okay? So we can add compute to that. We could do things like camera effects like depth of field. Okay, let's take it another step. We could do bloom. But none of these look super great. Okay, so now we're going to turn on RTX. So this is area lights with RTX. And notice the soft shadows. Some parts of it is well lit, and some part of it is kind of blurry and nice and soft, and that's the feeling that you get when you see a really nicely well casted shadow. Let's suppose we had more area lights. Okay. Now with more area lights, you would expect each one of the area lights to be able to contribute to lighting the scene. And so you could see now the penumbra and the umbra right here, nice and sharp, and this is nice and soft. You could see the light bleeding on top of the roof, casting nice shadows. So if you were to do this with traditional graphics, the way you would do it is to simulate that area light with a whole bunch of point lights. And all of those point lights would have to light the environment one at a time, and you would integrate that. Let's suppose we go do something even harder. So this is reflection. Reflections are hard to do using traditional computer graphics, and the way that they do it is to create an environment map, and that environment map would now be a texture map that's looked up. Okay, let's take another step forward, Omer. And this is diffuse reflection. Diffuse reflection, adding roughness to the ball. Okay, another one. Adding refraction. This is another ray traced effect that works incredibly well. However, there's something looks wrong down here, Omer. That doesn't look quite right. There's an effect called caustics as light accumulates. There you go. So that's caustics. This is a mixture of ray tracing and rasterization. Suppose we went to path tracing. Suppose we did global illumination. Wow. Ladies and gentlemen, all of this is just working right out of the pipeline, and this is the benefits. Okay, so we have computer graphics, traditional graphics with rasterization. We showed you depth of field rasterization with compute. We showed you area light rasterization, ray tracing, and compute. We showed you reflections, rasterization, ray tracing, and compute. And the compute in each case is to denoise ray tracing. Because the rays are bouncing all over the place. At some point, you could use AI or some heuristics to figure out what are the missing dots and how should we fill it all in. Now, the benefit is this. This is how we started. This is traditional computer graphics, rasterization, and shading, and wonderful materials. We could fake it. We can improve the looks of it with all kinds of trickery, and we all do that, and it makes video games look amazing. However, it's so brittle, and so many things you can't do, but you could turn on RTX, and it looks like this. Everything here is completely in real time, so off, on. Which one do you guys like better? Okay, so what we did is we put everything together into a really short clip. What you're about to see is completely in real time. For the longest time, real-time computer graphics has been really used for interactivity, design of CAD, use it for flight simulators, use it for video games. The market that relies on visualization, photorealistic visualization, is absolutely gigantic. However, it's never been able to use GPUs. It's never been able to have the benefit of acceleration because the requirements are photoreal. Unless you could do ray tracing and you could do global illumination with physically based materials and physically based lighting. Until you could do that, it's simply impossible to take advantage of acceleration for most of these markets. And they're all completely run on CPUs today. Architectural engineering and design. Unless it looks like it's going to look, it's really impossible to use the image. And today's architecture, they're not large brown buildings and large structural buildings. They're buildings that are basically gigantic products, beautiful, gigantic products. And they want you to feel the experience of being in it. And without understanding the effects of light and how light responds in that entire environment, it's really, really hard to convey the sensation that you would ultimately get when you're in the building. Visualization. Every catalog today is largely rendered. The reason why it's rendered is because it's more flexible, obviously, and because it's cheaper. And you guys know, of course, whether it's full feature-length animations or special effects, all rendered with large render farms. For the very first time, NVIDIA RTX is making it possible for us to bring accelerated workflows and acceleration to this market. It turns out this is the 70th birthday of Porsche, and they created an amazing trailer. I want to share it with you.
The speed of light, a universal constant, never diminishing, never ending. "70 years of unrelenting progress. The Porsche 911 Speedster concept. The speed of light."
Now, just imagine, in order to create that trailer, the reflections has to look right. The materials have to be physically based. So when light strikes it, it creates the right appearance. The reflections are dynamic. It's flowing over the car. There's global illumination, soft shadows, the little tiny creases, reflection and refraction off the windshield. This image is so subtle, it's simply not possible to rasterize it. Well, as it turns out, what you saw just now, it was not a movie. It's completely in real time. This is the work, again, of some amazing engineers and artists. We worked so closely with the team at Epic and the Unreal Engine team, the Porsche designers that were part of this project. They're so proud of it. I mean, this is just utterly shocking. Is Kim there? Where's Kim?
Yeah.
Kim, what do you think?
Unbelievable. You know, I've been in computer graphics now for 27 years, and it was a dream to see real-time ray tracing come true. And I think over the next decade, we're going to see such amazing capabilities of your hardware, powering, interactive experiences. Movies and games, they're going to look the same. Photorealism, absolute photorealism is within our grasp now. It's amazing. And I think AI for ray tracing, AI for computer graphics is also going to revolutionize the possibilities. So I think we're going to get movie quality within this new generation of cards. I think we're going to see movie quality in games as well as more enterprise-like applications like this.
If you would have projected from DGX Station to where we would have finally expected to see this on one graphics card, we expected something along the lines of 5 to 10 years. Because of two fundamentally new technology, we were able to bring it to today. And those two technologies is exactly what Kim was saying earlier, ray tracing acceleration with the RT core, and then deep learning with the Tensor Core. By combining those two technologies with what we did before, rasterization and shading and compute, all of a sudden we gave ourselves just an enormous boost, and we pulled in ray tracing somewhere between 5 to 10 years. And everybody is surprised. Everybody is shocked. All the developers we're working with, it's just amazing that we can basically cast as many shadows rays as we want. Reflection rays and refraction rays are much, much more expensive, but even then, we could cast a whole bunch of them. The ability to be able to do ray tracing at 10 gigarays per second is really, really quite powerful. What you're looking at on top is essentially what you would get if you had DGX Station. The architecture that's inside DGX Station for computer graphics is essentially what you're looking at, PASCAL. Okay? And with some of it is used for rasterization, some of it's used for shading, and a lot of it is used for tracing the rays. There's a few technologies that when in combination in this RTX platform, when you put them together, does this. A 6x speed up in computer graphics. Well, the way that it's done is we, number one, accelerate the ray tracing part of it. We still have to shade it, but the ray tracing acceleration is just incredibly fast. The second part is by using AI, we're able to render at a slightly lower resolution, but because we trained that model off of very high quality ground truth, we're essentially going to be able to generate the final image at a much, much higher rate. And so we call it DLAA. The combination of AI and ray tracing has made it possible for us in the Unreal Engine 4 with RTRT, real-time ray tracing, running on top of Microsoft's DXR API. This is basically today's most popular platform. We're able to take computer graphics and improve it by a factor of 6. Turing is 6 times Pascal. One of the most important things you'll see, and Kim was alluding to it, is that we're going to use AI in so many different parts of our graphics pipeline. One of them is anti-aliasing. We use a temporally stable convolutional autoencoder. We teach this autoencoder from ground truth that was generated from 64 samples, jittered samples of a rendering. You render the same image 64 times, we jitter the samples, and then we use a very high quality filter, and we combine it all together into one, and it becomes one frame of a ground truth. We create a whole bunch of those, and we teach this neural network how to take an image and automatically generate a much higher quality image. As a result, we could start with a lower resolution image, and the result is a higher quality than a higher resolution image. Really, really quite amazing. The power of deep learning. High quality motion image generation. We call it the NVIDIA DLAA, and that's what you saw in action. As a result, the combination of ray tracing, faster shading, DLAA because of the tensor core, these 3 processors working together, Turing was able to accelerate the rendering time by a factor of 6. Architectural design needs photorealistic images. These scenes, to an architect, has to be photoreal so that they could convey the sensation of the environment to their clients. To do this is incredibly challenging, and the reason for that is because in most of these rooms, light is largely indirect. It comes in, it bounces around, and it picks up the nuances of the surface it strikes. The light is indirect, materials are physically, obviously physical, and so they have different reflectance properties, and that gives you the sensation of a space. So this is the Rosewood in Bangkok. So we created this visualizer, and it's connected to Revit, in this case, and SolidWorks. Between SolidWorks and Revit, you could modify and edit right there in the tool, and it will show up instantly in the viewer time. And then it's rendered on RTX. Sean, go ahead and give it a try.
Yeah, that's exactly right. So we can see we have Revit open there. We're looking at the lobby scene, and at this time of the day, there's just not enough natural light coming in. So why don't we open up some of the skylights, and we can see how that affects the illumination.
Now, obviously, you can't fake this. Obviously, this isn't baked into the textures, and the reason for that is because you just place the lights. And you can modify the lights. You could change the time of day and get a sense of the feeling of this room. Look at that. Wow.
If we go a little deeper into the scene, we can see this kind of lobby feature here by the elevators. So we can import an object here from SOLIDWORKS and simply see how changing the materials in SOLIDWORKS actually changes the look and feel of the space.
This is Jeff Koontz's Love Shiny Dogs. Wow. You guys see what's happening? I mean, this is just amazing. This is like having a wormhole between SolidWorks, Revit, and this viewer. That's beautiful. Look at the reflection of the sun right back there. It's just incredible, the bloom there. Okay, ladies and gentlemen, using RTX for architectural engineering and design. We worked with Autodesk's Arnold team, and they've been working with RTX, and they're just completely blown away. In no time ever has it been possible to render final film production on a GPU. And the reason for that is because it just wasn't fast enough. It wasn't fast enough, and it didn't have large enough frame buffer to be able to hold all of the assets. It wasn't fast enough because so much of the time is spent ray tracing. Well, finally, with RTX, we've been able to do so. What I'm about to show you are several images of a shot. Every one of these frames were rendered on the Quadro RTX. Final film quality for the very first time. This is what you get when you have the world's first ray tracing GPU with 48 gigabytes each. And if you connect the two of them together with this incredible technology that I'm wearing called NVLink, you get 96 gigabytes of frame buffer. And so, for the very first time, we're able to ray trace final film production quality assets. Well, we created a server called the RTX server, and it's designed for production rendering with full global illumination. And this production server is really quite amazing. This one server with 8 GPUs will allow you to speed up your final film rendering. And it's designed to be remoted. It sits in a data center. It could be your render farm. It could also be your workstation. It could be your RenderMan workstation. It could be your Maya workstation. It could be your Nuke workstation. Every single application in the DCC universe is compatible with the software layer that we created called Quadro Infinity. You can put this in your data center, it becomes your workstation, and whenever you're not using it as a workstation, is your render server. The rendering time goes down from hours to minutes. And so let's take a look at what that means. Suppose, most of these data centers, as you know, it's not unusual for production cost to be $100+ million. And 20% of that, $20 million of it, is very typically assigned to the render farm. I'm showing you here just $2 million, 1/10 of a render farm. This is not quite a farm. This is probably just a garden. Okay? 240 dual CPU, 12-core Skylakes, 144,000 watts, $2 million. That's what you're looking at. If we wanted to have the same throughput on the RTX server, this is what it looks like. This is before. This is after. This is your personal render farm. And it's just a fraction of the cost. It only costs about 1/4 as much. It takes 1/10 the space, and it takes 1/10 the power. Each megawatt of power is $1 million a year. Most data centers have 10, 20 megawatts, and so you could imagine the cost as it goes forward. Saving money is one reason, but as we know from Blind's Law, whatever the budget is, the DP is going to want to use that full budget to maximize their creativity. And so let's take another shot at this. Suppose you had a constant budget of $500,000. So you had one server rack here for $500,000, another one for $500,000. You get 4 times the performance. The reason why it's so amazing is because each one of those DGXs allows you to create a 3-second shot. Most shots are about, call it 2 to 3 seconds, about 75 to 125 frames. Those shots now take 1 hour. Instead of a shot taking 5 hours or 6 hours, it now just takes 1 hour. It's going to completely change how people do film. The excitement from the DCC, the ISVs have just been incredible. Adobe Dimension is working on integrating RTX. Autodesk Arnold Pixar RenderMan, Chaos V-Ray, Weta, all integrating RTX. All of the DCC tools, CATIA, Siemens NSX, SolidWorks, integrating RTX. The number of software developers that have come out to embrace this platform is like nothing I've ever seen. And the reason for that is this. Everybody is under the constraint to deliver photorealistic images. Global illumination is now the bar. The Quadro RTX starts at $2,300. RTX 5000, all of that capability, accelerating rendering for final film, the ability to generate photorealistic images for architectural engineering and construction, DCC, generating photoreal images, not to mention real-time ray tracing for video games and interactive content. RTX 5000, 16 gigabytes, 32 gigabytes with a NVLink starts out at $2,300, 6 gigaраys per second. The 6000 is 24 gigabytes and 48 gigabytes if you use NVLink, has 10 gigaраys per second, $6,300. And then finally, the monster, RTX 8000, 48 gigabyte frame buffer. It's just gigantic for just $10,000. It's a steal. The important thing to remember is this: the more you buy, the more you save. Every single world-class global system maker has jumped onto RTX. You're going to have workstations. You're going to have servers of all different sizes. Quadro RTX is going to be available all over the world. So this is it. NVIDIA Turing, graphics reinvented. There's no question in my mind, this is the single greatest leap that we have ever made in one generation. This is the most important GPU we've created since NVIDIA CUDA. The Quadro RTX 8000, 6000, 5000, the world's first ray tracing GPU, supporting a complicated stack that has been integrated into ISVs all over the world. The Quadro RTX systems allows you to do 7 shots in one day. 7 shots in one day. Who doesn't want 7 shots in a day? And then for the very first time, after all these years, we've been able to build something that the visualization industry, the $250 billion visual effects industry, we can enable them to be accelerated so that we can change their workflow, so we enable them to do more with the same budget. Before I say goodbye, I want to thank all of you for coming to our launch. We're so excited about the Turing launch. I appreciate the support of literally every single developer in the DCC industry. The embrace that you have given us for NVIDIA RTX is nothing short of astounding. And the reason for that is I believe you all see, for the very first time, we could take a giant leap and redefine what computer graphics is. Computer graphics will never look the same again. I also want to thank all of the audience who are the pioneers of this industry. Because of the work that you have done, it has allowed us to stand on your shoulders to create what you see today. So ladies and gentlemen, I want to thank all of you. Thanks for coming to our launch. The team is going to show you something that is utterly unbelievable.